everybody. How's it going? So we want to pick up a new section, which doesn't seem like it has anything to do with what we've been doing so far, but it definitely does. We've been talking about critical numbers, absolute max, absolute min, relative max, relative min, increasing, decreasing, concave upward, concave downward, inflection points, the first derivative test, the second derivative test. It all has to do with applications of the derivative and graphing. And we need to discuss the definition of a limit at infinity and take some of those limits when it has to do with graphing. So in this section, we're not actually going to take any derivatives, which is surprising. We're going to go back to limits, but it's well placed because the next section covers curve sketching completely, and we need this in there now. So a definition of a limit at infinity. So L is going to be a real number, just a number. It's a y value. And we say the limit as x goes to infinity. Now that's the first time we've had infinity as our limit value. So the limit as x goes to infinity of f of x equals L means that, you're going to love this, for each epsilon greater than 0, there exists an m greater than 0, such that when f of x minus L is less than epsilon, whenever x is bigger than m. Now, I'm not going to make you memorize that. I just want to explain it this one time so you have it this one time and then not worry about it anymore. So first I'm going to draw a graph that as we go out to infinity, it has a limit of L. So let's just say the graph looks like this. Okay? And our L value is right here. All right. Now, here's what they're saying. Okay? Remember, epsilon is a really small number. Think about it as a distance. And they're saying the distance between f of x and L. Okay, so let's just say, here's my x value, which means right over here is my f of x value. And say, and this has got to be true for every single, it says for each epsilon greater than 0. So if we pick a really small number, I'm not going to pick a specific number, epsilon, okay, which is some distance away, okay, and it's saying the difference between f of x minus L, so this distance, let's don't pick epsilon on here, I'm going to confuse you if we do that. So the distance between f of x minus L has got to be less than epsilon. So right there, that's the difference in f of x minus L. So let's just say we picked epsilon super small, like a lot smaller than that. Then what would we do? We would pick a value further away than x. So let's just say there's an m such that the distance is less. So if I pick my m right here, okay, and I go up to my graph, and I come back over here, that distance could be less than epsilon. What if I picked a smaller epsilon? Then I would pick a number further out, and it would get closer and closer. And so that's our definition. So the difference between your function value and L can always be made smaller and smaller and smaller by picking a larger and larger and larger x value. Now, I'm not going to draw a picture for the other way, but it's the same idea. It says the limit as x goes to negative infinity of f of x equals L means that for each epsilon greater than 0, there exists an n less than 0, such that when f of x minus L is less than epsilon, whenever x is less than n. So you're going the other way. We're going to negative infinity. You have an L value. You just pick n further and further down the line in the negative area. Okay? So that's your definition. It's your official definition. I'm not going to make you responsible for that. I just want you to be able to do the problems in this section, which I think you'll find pretty reasonable. We've got methods. By the way, I do want to point out that I get this mixed up all the time. You have two things. You have limits at infinity, which is what we're doing right here. This is limits at infinity, and that's when you have infinity or negative infinity as your limit value. That is opposed to infinite limits. Now, an infinite limit is when you take the limit as x goes to c of your function and you get either plus or minus infinity. Really, it means the limit does not exist, but it's how it doesn't exist. And again, I get the names of those mixed up all the time. Not the methods, not how to solve it. I just will use, I often call limit at infinity an infinite limit, but it's a limit at infinity. The answer is actually not infinite. It's a specific value. So our first official problem is evaluate the limits numerically. Remember in our very first section, or second section, when we started talking about limits, and we talked about evaluating them numerically, which is basically you just plug in a number closer and closer to your C value. Well, that's what we're going to do here. We're going to plug in a number closer and closer to infinity, like we're going to actually get there. So tell me, what numbers would be good to plug in? Your first thought might be, let's plug in 10, and then plug in 100, and then plug in 1,000, and plug in 10,000. Now you can be more creative than that, but I'm not. Plug in 100,000. That's going out to infinity, right? Definitely. All right. So what I'm going to do is take that 10 and plug it into every x value. So this would be 10 times 10 divided by the square root of 10 squared minus 1. That would, of course, equal 100 over the square root of 99. I typed that in my calculator, 100 divided by the square root of 99. And I'm using a calculator I don't typically use. And it didn't work. That's what I'm supposed to get. So I got 10.05, and that keeps on going. 10.05, ... I guess I should say 0503. Should take it on out there. And then the next problem I would do 10 times 100 divided by the square root of 100 squared minus 1. Now, I'm not going to type all these in right now, because lucky for you, I've already got them simplified. And so when I plugged in 100, I got 10 point, now watch this, 0, 0, 0, I got to count the zeros, 1, 2, 3, 4, 5, and then a 5. And then when I plugged in 1,000, again, that reminds you that'd be 10 times 1,000 divided by 1,000 squared minus 1. And that gave me 10.1, let's see how many zeros this has, 1, 2, 3, 4, 5, 6, 7, 5, all right, and then 10,000, I got tired of even typing it in, because you know what? I can tell what it's approaching, right? This is 10.0503, this is 10.00005, probably 03, 10.0503, you get the point, this is going to 10. Without a doubt, this limit is 10, okay? Now the other way, same idea, except we're going to, notice, negative infinity. So I need to plug in numbers approaching negative infinity. So first try is plug in negative 10, and then maybe negative 100, negative 1,000, negative 10,000. I have a feeling it's going to work similar to the other one, negative 100,000. So careful with your signs. That would be 10 times negative 10 divided by the square root of, now, when I square that negative 10, it turns positive. That's going to be a positive 100, but we're going to have a negative 100 in the numerator, minus 1. Now, the only difference between these two calculations, right, is this negative sign right here. So I am guaranteed that this is negative 10.0503. You don't believe me? Just plug it in. Always just plug it in if you're not buying what I'm saying. So next is negative 10.0000. Again, 1, 2, 3, 4. There's 5 of those. 5. And this one would be negative 10 point, and then 7 of those. 5. Yep. Okay. And then the next one, again, because I didn't bother to plug it in here, I didn't plug it in here as well. So what is this approaching? Well, it looks to me like it's getting closer and closer to negative 10. All right, so you can always evaluate these numerically. That ought to be a relief, because that's the easiest thing ever. You just take the number, plug it into the function, plug in a bigger one and a bigger one and a bigger one, or if you're going to negative infinity, smaller and smaller and smaller, and you can get a result. Now, I am going to show you how to do these numerically, specifically this one. We're going to revisit this one later in the lecture. But if all else fails, you can always go to a numerical version. Hey, you want to see what the graph looks like? This is the graphical version. So let's take a look. Look, there's your graph right there. So this is the graph of 10x divided by the square root of x squared minus 1. Remember, as we got bigger and bigger and bigger, our y values were getting closer and closer to 10. So remember, here's our 10 right here. they were above 10. Remember 10.0005, 10.0005? There we are, right in there, getting smaller or closer and closer and closer to 10. It looks like it sits right on 10, but it really doesn't. It just gets there so quickly. And on the other hand, this is negative 10. So as we go out to negative infinity, what are my y values doing? They're getting closer and closer and closer to negative 10. Now what you have going on here is your classic horizontal asymptote. You've heard of this before, not in terms of limits, but that's actually how you define a limit. So as we go across right here, notice there is a horizontal asymptote at positive 10, and there's also a horizontal asymptote at negative 10. So a graph can have more than one horizontal asymptote. As you go out to positive infinity, it could have one value, and as you go out to negative infinity, another value. And here's our official definition of a horizontal asymptote. So the line, and this is important, the line y equals L. So horizontal asymptotes are always written in the form y equals, just like vertical asymptotes are x equals, horizontal asymptotes are y equals. When the limit as x goes to negative infinity gives you a real number, or the limit as x goes to positive infinity gives you a real number. So back to comparing the idea of infinite limits and limits at infinity. Remember infinite limits, when we got plus or minus infinity as an answer, gave us vertical asymptotes, and those are x equals. Well, limits at infinity, when you take limit as x goes to infinity or minus infinity and get a number, kind of the opposite idea, then that gives you horizontal asymptotes, and those are y equals L. Now here's a theorem that'll come in handy. If r is a positive rational number, okay, so r is positive and it is a fraction, not just any old real number, but it's a rational number, so it's a fraction. Could be an integer as well. And c is also a real number, okay, it doesn't have to be a fraction, then the limit as x goes to infinity of c over x to the r is equal to 0. Now let's think about that. What's going on here? So if x goes to infinity, and you're plugging in infinity right here, so that's like thinking c over infinity to the r power. Well, that's like c over infinity, right? Infinity raised to some power is still infinity. It may just be bigger. It could be smaller depending on what your r value is. Because remember, r could be a fraction like 1/2, so the square root of infinity is smaller than infinity, but it's still infinity. Okay, but anyway, so c over infinity goes to 0. That makes sense, right? You've got a number sitting on top that doesn't change, but this number on the bottom you imagine is larger and larger and larger and larger. That must go to 0. Same thing on the other side. So if I take c over negative infinity and raise it to the r power, that's like saying c over negative infinity. So imagine keeping c fixed like 5 and making this denominator negative 10, negative 100, negative 1,000, negative 10,000. That goes to 0. So anytime you have a number over infinity, and this we have discussed before, that goes to 0. All right, so let's do a problem, finally. So we're supposed to take the limit as x goes to negative infinity of 5 over x minus x over 3. Now, you are literally imagining plugging in infinity into this. You could do this numerically by picking smaller and smaller numbers like negative 10, negative 100, negative 1,000, negative 10,000. But think about it this way. So, first of all, we've got a sum difference rule. So I can say the limit as x goes to negative infinity of 5 over x minus the limit as x goes to negative infinity of x over 3. Okay, then you're plugging in negative infinity right here. That's 5 over negative infinity. Now, we have a theorem for that. We don't have to go far to look for it. Just look up. Okay, we know that's 0. Minus the limit as x goes to negative infinity. Okay, now if you plug negative infinity in here, that's like negative infinity over 3. Now, if you take an enormous number and divide it by 3, or a negative enormous number and divide it by 3, it's still enormous, right? Okay, so this is still infinity. So this is like 0. These two negatives turn positive, And again, think about that as infinity over 3. That's really 0 plus infinity, which is infinity. Now, what does that mean? That means this limit does not exist. Okay? That's what's important. So this does not have a horizontal asymptote. This limit does not exist. By the way, to throw out lots of terminology, think about what this is. This is an infinite limit at infinity. It's both of them, right? We got infinity as an answer, and we're taking the limit as x goes to negative infinity. There you go. All right, so here's a third example, C. We're going to take the limit as x goes to negative infinity of 4x squared plus 5 over x squared plus 3. Now, it's not as straightforward as the last one. Now, if you want to, you can plug in smaller and smaller values. In other words, negative 10, negative 100, negative 1,000, negative 10,000, and find it numerically. You could also graph, but I have a method for you that I don't have typed up. I have a method. So here's the method. If you have a fraction like this, okay, and you multiply the numerator and denominator, I know that is so hard to read, I'm sorry. The numerator and denominator by 1 over x to the highest power in denominator. You'll see it happen, okay? And then simplify. Then you can use your theorem that we just used a minute ago to evaluate this limit. So, first of all, the highest power in the denominator is squared. So what I'm going to do, don't forget your limit in the front, x goes to negative infinity. I'm going to multiply the numerator 4x squared plus 5 times 1 over x squared. And I'm going to multiply the denominator, x squared plus 3 times 1 over x squared. Now, again, my decision came from the denominator, not what was in the numerator, but only from the denominator. Now, why did I do both the top and the bottom? Because I'm really just multiplying by 1. So I'm not changing the value of our expression up there. I'm just multiplying by 1 over x squared divided by 1 over x squared, which is 1. Now, I need to distribute that 1 over x squared inside the numerator and the denominator. So now my problem is the limit as x approaches negative infinity. Now 4x squared times 1 over x squared is 4x squared over x squared, plus 5 times 1 over x squared is 5 over x squared. Divided by denominator, x squared times 1 over x squared is x squared over x squared, plus 3 times 1 over x squared is 3 over x squared. You okay with that? Now I simplify, so I'm at this stage. We've got the limit as x approaches negative infinity. Now 4x squared over x squared is 4, plus 5 over x squared cannot be simplified. X squared over x squared is 1, plus 3 over x squared cannot be simplified. Now, normally, we're trying to get rid of this mess we have going on right here, which is a complex fraction. But for these problems, our goal is a complex fraction, so we can use our theorem before. Remember this theorem in orange, that if you have a constant over infinity or a constant over negative infinity, either way, that goes to 0. So back over here, look at our zeros. Look right here. Constant over, we're going to negative infinity. I plug it in, I square it, it goes to infinity. That's 0. Constant over, again, I'm plugging in negative infinity, which squared goes to positive infinity, it goes to 0. And it doesn't matter whether it's negative or positive infinity in the denominator. If you have a constant over plus or minus infinity, it always goes to 0. So what are we left with? We're just left with the limit as x goes to negative infinity of 4 over 1, which is just 4. So this limit is 4. It also means we have a horizontal asymptote as we approach negative infinity of our x value. Our y value is 4. Now, do you recognize this problem? It says find the following limit. There it is, 10x over the square root of x squared minus 1 as we go to infinity, and then as we go to negative infinity. This is the first problem that we did numerically in this video, and I'll go back and switch it back to that view in just a minute, but let's follow the steps I just showed you. So again, if you have a fraction and you have an x to a power in the denominator, you should multiply both the numerator and the denominator by 1 over x to that highest power. Now in this case it's a little bit different, but it still applies. So this is 1 over, now x squared is the highest, but you know there's a square root right there? I know you see it. So this is going to be the square root of x squared, and 1 over the square root of x squared. Weird, huh? Okay, we're all right, we got this. Now, still have the limit as x approaches infinity. Now notice in the numerator and denominator I have exactly the same thing. The square root of x squared is just x if we're going to plus infinity. Okay, so the square root and the square cancel each other out, and since we're going to positive infinity, that's a positive x. So this is the same as saying 10x times 1 over x. Now the denominator, I want to leave it because the only way to multiply a square root, distribute inside, is with another square root. So I can even think about this square root that's down here is really over the whole thing because that's a 1 up there. And then I can distribute that inside this square root. If that weren't under a square root, I couldn't do that. Okay? But I can because it's under a square root. So this is the square root of x squared over x squared minus 1 over x squared. So again, that one times that one, and that one times that one. Now when I simplify, don't forget your limit in the front as x approaches infinity. Now 10x times 1 over x is 10, which is nice. And in the denominator, I have the square root of x squared over x squared is 1 minus 1 over x squared. What do I do now? Here I am again, I have a constant over infinity. Remember, we have a theorem that says if you have x to some kind of rational exponent, and 2 is definitely a rational number, then that goes to 0. I love doing that. That goes to 0. That's it. Now, what are we left with? Well, this is the limit as x goes to infinity, because we took the limit of this, but not the rest of it. 10 over the square root of 1, which is just 10 over 1, which is just 10. Okay, now if you recall, and we'll flip back to it after we do the next problem, that's the answer we got when we did it numerically and when we looked at the graph. Now the next problem. So I'm going to do the same thing. I'm going to multiply by the highest power in the denominator, which is going to be 1 over the square root of x squared and 1 over the square root of x squared. So when I simplify, I'm taking the limit as x approaches negative infinity. So again, notice the first step does not matter if you're going to plus or minus infinity, okay, at all. Now, I've still got my 10x up here, and I've still got the square root of x squared minus 1 in the denominator. Let's check out the denominator first. Another way to write that, because there is a 1, is the square root of 1 over x squared, like that. Okay, you don't even have to do that. You could say 1 times the numerator over the denominator, and since they're both under square roots, you could write it as 1 square root. So you don't even have to go this far with it, okay, because that's a 1 up there. You can distribute it, or just multiply it out front, and then poof, it's gone. Now here's where this problem gets fun. The square root and the square cancel each other out. But now when you take the square root of x squared, by definition, that's always a positive number, right? Because the square root's always a positive. So to fix that issue, when I simplify this, 1 over x, I have to make that a negative x, because you're talking about as x's go to negative infinity, that x is a negative number, okay? Yeah, I think that's the smartest way to think about it. Really what's going on is this is positive and this is negative because we're going to negative infinity, and these two guys are going to cancel each other out and leave a negative. That's the better way to think about it, because when you take the square root of x squared, it's always positive. And if I cancel that x and that x, I'm still missing an important thought that x is going to negative infinity, so x is actually a negative number. So you're canceling this negative number with this positive number, and it leaves a negative. So this is the problem with this particular problem, is when you're going to negative infinity, you got to be super careful with your x values and dealing with even radicals. So what I'm left with now is the limit as x approaches negative infinity. So the x's cancel, but it left that negative. So this is negative 10 over. Now at the denominator, we don't have anything to be concerned about. Okay, because all that is still squared. You're multiplying under a square root, so it's going to be x squared over x squared minus 1 over x squared. Now I get to use my theorem that says if I have a constant over infinity, because when I plug negative infinity to that, that goes to 0. So I still have the limit as x approaches negative infinity of negative 10 over the square root of 1 minus 0, which is just going to be negative 10 over the square root of 1, which is negative 10. Now, to me, that's one of the most confusing problems that you run into in this section when you're dealing with square roots or any even radical, and you're going to negative infinity. All in the denominator, all that's positive because you're talking about square roots, so those results are positive. But in the numerator, this guy is positive, where this guy is depending on the value you're going to. So if you cancel this positive or negative x with this strictly positive x right here, it's going to leave that negative value. So the first time I explained it wasn't really the best way to explain it. But after I explain it again, that's really the way that we need to look at it. Okay? Now, I told you I'd revisit it the first time, so let's scroll back, or I'm going to scroll back. You're just going to wait for me to do it. And these were the values we got. Remember, we went to 10 and negative 10 as plus or minus infinity. And then there's your graph. As you go out to as you go out to plus infinity, the y values go to 10. As you go out to negative infinity, the y values are a little less than negative 10, and they get closer and closer and closer to negative 10. And again, horizontal asymptotes. If you take the limit as x goes to plus or minus infinity and you get a number as your answer, that means you have horizontal asymptotes. Now here's 3 examples for you. I like to only put one example on a page when we have so much work to do, but I want to be able to compare them. Look how they look almost just alike. What varies, of course, is what's in the denominator, but I want to compare and kind of come up with a method for thinking about this. And you may recall finding horizontal asymptotes in pre-calculus. That applies to this, and we'll take a look in just a minute, but we're going to do this the formal way. So first of all, I'm supposed to multiply by 1 over the highest power of the denominator. How do I know when to do that? Listen, if you're going to plus or minus infinity, and you have a rational function, fraction like this, that's when you need to do it. So we're going to multiply the numerator by 1 over x squared and the denominator by 1 over x squared. And that's the method because it works. So we've got the limit as x approaches infinity. Then when I multiply 5x to the 3 halves, and I'll write it down. So we have 5x to the 3 halves divided by x squared in the numerator. And then you have 4x squared over x squared plus 1 over x squared. Now I keep simplifying. That's the limit as x goes to infinity. Now what do we do with these exponents? I got a 3 halves and a 2. I subtract, right? So 3 halves minus 2. And so that's going to give me 5 over x to the 1 half. Does that sound right to you? So really, 3 halves minus 2 is negative 1 half, and I took it to the denominator, or 2 minus 3 halves is 1 half. Make sure you follow that. The x squareds cancel, that gives me 4 plus 1 over x squared. Now, I don't want to deal with negative exponents in this situation, and that's why I wrote it like that. Because, remember, we want to use that theorem, that awesome theorem that says if you have a constant over infinity. Now, why is that infinity? Because I'm plugging in infinity, so that's 0. And that guy right there is 0 as well. So that gives me the limit. I need to change colors back on you. That gives me the limit as x approaches infinity of 0 over 4 plus 0, which is just a big fat 0. So we have a horizontal asymptote in this situation. As we go out to plus infinity, our y values are going to 0. Now compare that to the next one, which looks almost just like it, but are highest power of the denominator is 3/2. So I'm going to multiply the numerator by 1 over x to the 3/2. I'm going to multiply the denominator by 1 over x to the 3/2. So I get the limit as x approaches infinity. Now, 5x to the 3/2 over x to the 3/2 is going to give me 5. Is everybody comfortable with that? I'm hoping so, because the x to the 3/2 just cancel. In the denominator, I'm distributing. Okay, so 4x to the 3/2 over 1x to the 3/2 just gives me 4. But don't forget, you still have to multiply 1 times 1 over x to the 3/2. Then I get to use my fancy theorem that says if I have a constant, which is 1, over x to a rational exponent, okay, as long as that is a fractional exponent, then that goes to 0. Okay, and it's got to be a positive rational exponent. Let's go back and look at that. Yep, positive rational exponent. And that's why I didn't want to deal with that negative right over here, that negative 1/2 we had right here. Didn't want to deal with that. To be able to use my theorem, I need a positive exponent. So that gives me the limit as x goes to infinity of what's left, which is 5/4, which is just a constant. So 5/4 is my answer. Now, you may be noticing some patterns. I will mention them in just a minute, but let's do our last problem. Let's go with gray. Okay? And so, the square root of x, let's think about that as x to the 1/2. Okay? So I'm going to multiply the numerator by 1 over x to the 1/2, and I'm going to multiply the denominator by 1 over x to the 1/2. I'm going to rewrite my limit, so don't forget what I'm doing as x goes to infinity. Now, we don't have any of that negative stuff like we did in the last problem to do with, because all these are going to positive infinity, okay? Now, when I multiply the numerator, 5x to the 3/2 times 1 over x to the 1/2. Let me just write that, just in case you get lost in the mess. That's 5x to the 3/2 divided by x to the 1/2. That's just the numerator. The denominator, we're going to have 4 square root of x over x to the 1/2 plus 1 over x to the 1/2. I guess I didn't discuss why I did x to the 1/2, but you see, right? Because that's square root of x, which is x to the 1/2. Now, I want to simplify this as much as possible. This is the limit as x goes to infinity. Now, the x to the 3/2 and the x to the 1/2 give me 5x to the 1/2 power. No, 5x to the first power. Right? What I'm doing, I'm subtracting 3/2 minus 1/2 is 2/2, which is 1. In the denominator, the square root of x and x to the 1/2 cancel to give me 4. And 1 over x to the 1/2, I'm just going to write it as 1 over x to the 1/2. Then we get to use our theorem that says if we have a constant over an x to a positive rational exponent, that goes to 0. And that's the only one I have. So now I'm still taking the limit as x goes to infinity of 5x over 4. Now when you plug infinity in, imagine this, you plug in infinity right there, that's going to be 5 times infinity divided by 4. What's that going to give us? How about infinity, right? 5/4 infinity is still infinity. So this limit does not exist. This is another one of those infinite limits at infinity. Love that. Okay. So this had no horizontal asymptote, whereas these two did have a horizontal asymptote. Now I want you to remember, if you can, back in your pre-calculus algebra class, we talked about horizontal asymptotes, and there were 3 cases that we dealt with. Remember when the degree of the numerator was smaller than the degree of the denominator. Like in the first case, it was automatically y equals 0. When the degree of the numerator was the same as the degree of the denominator, it was always y equals leading coefficient over leading coefficient, 5/4, okay? And then finally, when the degree of the numerator was larger, 3/2 than the degree of the denominator, which is a 1/2, by the way, because of the square root, then there is no horizontal asymptote. And please do remember, if you are asked to calculate horizontal asymptotes, this asked to calculate limits, and that was it. If you were asked to calculate the horizontal asymptote, it would be y equals 0 in the first case, y equals 5/4 in the second case, and then there is no horizontal asymptote in the third case. I hope that gave you some perspective and dealing with those fractional exponents as well. Still got 2 more problems, and then we can call this video done. Now you know I can't let you escape without some trig, so here we go with our trig. We got the limit as x goes to infinity of cosine of 1 over x. What to do? What to do? So I know you might be thinking, if I plug in infinity right there, that's going to give me a 0, and yes, that's exactly what you do. We have way back, because it's going to feel like forever ago, a composite functions limit theorem that says that you can take the limit inside the outside function. So this is what you're thinking about. We're taking the cosine of the limit as x goes to infinity of 1 over x. And you need some brackets or something in there to make that make sense. You can do that. That is what the theorem states. So if we take the limit as x goes to infinity of 1 over x, then we get to use our awesome theorem that says if you have a constant over infinity, that's 0. So this is the same as evaluating the cosine of 0, and we all know the cosine of 0 is 1. Now, maybe, just maybe, you would like me to go to Desmos to see that graph, just so you feel just a little bit better about it, because I know sometimes trig functions just don't feel as comfortable as some of the other functions. So let's just take a look. And I hadn't been to Desmos in this video yet anyway, so I need to. All right, here you go, folks. look at this mess. So notice how I have it typed on the left. This is y equals cosine of 1 over x. I don't think those extra parentheses around the x are required. I could get rid of those. I'm not really sure why they ended up there, but notice it's still the same graph. That's not the issue. Let's zoom in to take a look at it, because it is crazy looking. Look at that. It's very similar to sine of 1 over x. Come on, let me move it over. There you go. Okay, see how it isolates forever in the middle. And keep in mind what we were trying to do. If you go back and look at your problem, we were taking the limit as x goes to infinity. So we could care less about all this craziness happening in the middle. What we were trying to do is figure out what's happening way out here. Like as we go to infinity, and I'm just cruising on, I'm only at 7.5. I'm a long way from infinity. Still a long way from infinity. But look at what the y value is doing. All you see is that red line. Notice it up there to the left, right over here. I'm circling for you. That's approaching 1. So as I go farther and farther, what'd I do? What'd I do? Okay, I'm sorry, it moved down. Some crazy sliding going on. So look how close it is to 1 now. I can't even tell the difference. You remember what we got for our value, our limit value was cosine of 0. Did I get 1? Do you remember? Check it out. I did get 1. I couldn't even remember once I got that crazy graph up. I couldn't even remember what my answer was. So cosine of 0 is 1. You know that. So cosine's the x value on the unit circle, and that is 1. So that it's a neat graph. What's happening in the middle is really spectacular with all that oscillation. The fact is, we didn't care about that. We wanted to know what's happening as x goes to positive infinity. And the larger and larger values you plug in, the closer and closer that graph gets to 1. Let's do one more problem and wrap this up, okay? So got another trig function for you. We're taking the limit as x goes to infinity of x minus the cosine of x over x. So when you look at this, don't freeze up. We know what to do. Now we have a rational, sort of a rational expression. It's a rational expression with trig function in it, but the method is the same. So we're going to do what we did before. We're going to multiply by 1 over x in the numerator and the denominator. Where did I get that from? I'm looking at my denominator only, and I'm multiplying by 1 over x to the highest power in the denominator. So this denominator is why I picked 1 over x, not because of anything in the numerator. Then we simplify. In the numerator, I must distribute. In the denominator, I just multiply. So we're taking the limit as x approaches infinity. Now, x times 1 over x is x over x. I know you know that's 1. And then cosine of x over x divided by x over x. I'm just taking it way on out there. You don't have to show me that step. I do understand that that is just 1. That is minus cosine of x over x, and that is 1. Okay, now here's where it gets interesting. The 1's great. The thing is, what do I do with this? You know, the cosine of x is not a constant. You know, we have that theorem that says if you have a constant, which is just a number over plus or minus infinity, that goes to 0. But what about that? Well, here's what I want you to think about. Cosine of x. Y'all know what cosine of x looks like all by itself when you graph it. What's the biggest value cosine of x could possibly be? So you're thinking along the unit circle. What's the biggest answer on that unit circle that cosine ever is? And it's 1, right? What's the smallest value cosine of x ever is? And that's -1. In other words, the range for cosine of x, and again, if I graph it right down here, you know, it looks like that. Biggest it ever is 1. Smallest it ever is -1. And that's still over x. Now imagine x is still getting bigger and bigger and bigger and bigger. So even though this value up here is not fixed, it's not a constant, fact is that still goes to 0 because it's never going to get bigger than 1 or less than -1. So this number continues to get larger and larger and larger, and up here it's between -1 and +1 no matter what. Therefore, that goes to 0. So what are we left with? Well, we're still left with the limit as x approaches infinity. We've already used our theorem, so we've already plugged in infinity here, but we haven't in the others yet. But that just gives me 1 because it's a constant. Now, can't let you out of here without showing me this graph, or showing me this graph. You might not care, but I want to see it. So we're going to graph x minus cosine of x and show that when we go out to infinity, our answer is 1, and then be done with this video. Alright, so I'm in Desmos, and I typed in x minus the cosine of x over x. Again, notice all the parentheses I have where I typed it in to the left, because I want to make sure that Desmos understands my input into the cosine function is x. But then I also had to divide that entire numerator by x, so I needed that extra set of parentheses. And look at this lovely graph. So it's kind of wavy. Notice it's got a vertical asymptote at 0. Not surprised, because the denominator is equal to 0. We have 1. But remember what we were doing. We were finding the limit as x goes to positive infinity. So if I take a look out, so this is what's happening in the center. But what's happening as we get closer and closer to infinity. And notice how that's kind of wavy. It's really a neat looking graph. But as we get further out, see how the waves are not waving as much? And what's that approaching? So we're out at 60 now. And it's zooming out for me. I'm actually, or it's getting confused because it's having to recalculate every time I move. But we're approaching 1. So look over here in your scale on the left over here. So that's 5 up there. So we are definitely approaching 1 as we go out to the right. Okay, now let me move back. Bear with me, and it's probably hard to watch. Okay, now what's happening as we go to negative infinity? I didn't ask that on the problem, but look, as we go to negative infinity, notice how the graph is also going to positive 1. You have to look for the scale on the right. Actually, my video doesn't go that far, but this is up here, the first more bolden line is 5. And so, once again, that's 1. You get the same limit as you go to plus or minus infinity. I'm going back to the origin there so you can see they both go up to 1. And what's happening is all those wavy bumps just get more and more, get lower and lower and lower to eventually that it approaches 1. Okay, I hope you enjoyed this video and you got what you needed to out of it. Our next video is going to be awesome. It's a summary of curve sketching. So basically, if you're having any trouble with 3.1, 3.2, 3.3, 3.4, and this is 3.5, you need to get that straight first, because